Hi everyone, the three of us. How are you doing today? What I want to start with while we're waiting for people to come in, I did want to review a number of things I left outstanding from last class, but I spoke with a student yesterday asking for me to solve some of the test problems, and the one in particular was the one, and I did tell you I was going to look at that as well. I'm just thinking how I can put the question here. But this is the one about the boxes. I'll just, I'll outline what we know. So the probability you're told that there's a yellow ball, well, with all the information given, I can figure out that the probability, well, maybe I won't write it like this because that might even further confuse people who are already confused or not sure. So the probability of a yellow ball is going to be 1 in 10 because one of the 10 balls is yellow. So the probability of not a yellow ball is 9/10. And then for box 2, you're told the probability is 2. So the probability of not a yellow ball would be 8/10. And then for the third box, there are 3 yellow balls out of 10. So not a yellow ball would be 7. And finally, the fourth box, the chance is 4 out of 10. So the probability of not a yellow ball is 6 out of 10. So the probability of exactly one yellow ball it can become complicated because you want to think of all the combinations. But I've already reduced us to just looking at yellow and not yellow, so that simplifies things. That simplifies things a lot. So you have to think of the different events that would make it be exactly a yellow ball. So the chance of exactly one would be the probability that the choice or the selection from box 1 is yellow and no yellows from all the other boxes. Or the event, and I want to find the probability. I mean, I could write this out as a long statement, but I'll cut it short. Or maybe I won't. Let's see. Let me think. I'm going to write it up as events. So I'll say that this is going to be the probability of the event yellow from box 1 and no yellows from all the other boxes, or yellow from box 2 and no yellows from the other boxes, or yellow from box 3 and no yellow from the other boxes, or yellow from box 4 and no yellows from the other boxes. And I want to find that probability. So the and would mean multiply because these are independent draws, because I'm drawing from box 1 and the draw from box 1 doesn't affect the draw from the other boxes. Or the selection from box 1 doesn't affect the chances of selection from the other boxes. So that's a multiplication between those. The or means add. So I'm going to take the multiplication of these plus the multiplication of these plus the multiplication of these. So that's how it works. So yes, this was challenging, but I had to give a couple of challenging questions when I think the test is pretty straightforward and I give you so much time to work on it. So some people would have taken some time. There are some I'll have to look at what you guys wrote, but this is how you would approach this, rather than as opposed to writing all the possible combinations, because that can be very messy. You'll see there's thousands of combinations. So what's the probability of this? Well, I'll make some space here. So the probability of this I'll just do this. I'll do this. This is a yellow from box 1, chance is 1/10. And then I multiply that with the probability of no yellow from the other boxes. So the first one would be, so there's no yellow from the second box, that's 8/10. No yellow from the third box, that's 7/10 and 6/10. I multiply all of those. And then the next one, I'm going to add that to 2/10 times 9/10, 7/10, and 6/10. And then the next one, from the third box, the chance is 3/10, and multiply that by 9/10, 8/10, and 6/10. And then finally 4/10 times 9/10, 8/10, and 7/10. And the best way to do this so it doesn't get messy is to leave it as fractions. So this is 336 over 10 to the power 4. This one is 756 10 to the power 4. Then 1296 10 to the power 4. And 2016 10 to the 4. Then maybe there's an easier way to do this. I don't know. But when I just looked at this before the class, this is what I came up with. So you add it up. You add those all up. And sum the numerators. You get 4,404, and the denominator is always the same. And you get the answer, 0.4404. How's that? How's that explanation? So I've used the rule of independence. I've used the rule of joint events, all in one problem. Complementary events. I've used all my rules here. These are complementary events. Reducing the problem to a simpler problem we recognize. Once we get the momentum, we can solve this. So there's another question about what's the chance of at least So that's another question that I ask you. What's the chance at least one yellow? That would be the 1 minus the probability of no yellow balls. Or the probability all selections are not yellow. Okay, so you think you can do that? Can you guys do that without me, or do I need to do that one? Okay, so all selections being not yellow would be these events here. Not yellow, those are their probabilities. So the answer should be, you guys can tell me if I didn't check this. This would be 9/10, 8/10, 7/10, and 6/10. And so that would be 1 minus whatever that is. Can you guys get this now? What do you get? Yeah, that's what I get too. 0.6976. Was that the answer, Valeria? So it's like 70%. Was that the answer on the test? Okay. So another way to, so this looks more like what we did last time. I could also write these events as, I could say, this is the event Y, not Y, not Y, not Y, right? And this one is Y, I mean not Y, Y, not Y, not Y. But I put it in words instead. And then this one would be Y, not Y, not Y, but then Y and not Y. And this one would be y, not y, not y, not y, and y. So I put it in words and symbols for you. And this one would be all not y. Okay. Let me see, I'll double check. So I'm not saying that it's easy. It's a pretty comprehensive problem. It involved all the rules. But in a test that I give for such a duration, you know, you can be expected to do that. But now you have a better, I hope you have a better description of how to tackle that. Yeah, 0.7. That's the answer. So don't get frustrated. You're just learning. If you didn't get it, you're still learning. The key was this here, setting this up. Because usually I was looking at, well, I did have the occasion where we looked at heads and tails, so yes, this should be familiar, but my approach was purely on using the probability rules here. I didn't demonstrate all possible outcomes. Okay, so that is done. How is everybody about that? There was another question. The normal bottle. Okay, so if you got that, I want to look at the last or one of the problems in normal distribution. I can't really tell you which one it was because everyone had the questions randomized and shuffled, so everybody's questions appeared as different numbers. And so this was one of the norm problems. The contents of a bottle of water follows a normal distribution with a standard deviation of 4. Now, I didn't tell you about the mean. I didn't tell you about the mean, so I need to, if you didn't get this, I'll show you how to get this. So when I say within, when I refer to, so the question is, what proportion of bottles have fill volume within 1 milliliter of the mean? So what I want to know is the probability that X is mu minus 1, between mu minus 1 and mu plus 1. So when I standardize that, notice the mu is not necessary. I don't need to know the mu to solve this. I standardize it So yeah, that's kind of a trick you need to know, and you can practice that. There are exercises in the homework like this, I'm pretty sure. So now you see these cancel, so it doesn't matter. So you could have started here. Oh, I have the Z, so I can put that in. So you could have started here like this. But it's okay. You can go through the steps now that you know what to do. And so it's the probability is between negative 0.25 and 0.25. So then you look it up on the table. What do you get? You guys will have to tell me. It's quite high. I mean, it's for being on the left side. So this would be Is that correct? Nobody? No one's helping me? So this one is 0.5987. And when you subtract them, you get the answer. You could do it in Excel. I just did it in Excel because I don't have the table handy. Okay, and that's the answer. Any questions? Any other questions about the test? So there's a trick here you need to know. makes sense when you know what you're doing. It doesn't seem like a trick, but when you don't know what you're doing, it's tricky. So I'll give you that. All right, so let's go to the notes next. So what I wanted to do was look at this exercise. We'll go in order. This 104, this is 10 to the 4. It's not 104. Is that what you're asking about, Lydia? It's 10 to the power 4. Because it's 10 times 10 times 10 times 10. Is that better? Okay. So let's look at this first. Unless you understood the solutions, how many of you want me to try this one or solve this? All right. I'm going to solve this, then I'll go and look at a little bit more at the base rule and then a little bit more at the rules of mean and variances problems. And then we'll move into the binomial, and I'm sure we'll finish that today. So then tomorrow, Wednesday, we focus on SDS. SDS has some videos, so you guys can watch those in advance of the class, hopefully, or after the class. And then we start inference on Thursday, and we have Thursday and Friday exclusively for inference. Okay. All right, so here, this is another box problem. These are the ball numbers, balls in a box. And this time I want to demonstrate all the possible outcomes. There's only 2 boxes, so this is much more feasible than 4 boxes, like the exercise that I did from the test. So what I'll do is use the matrix, and I'll call this box 1 and this box 2, and put the possible outcomes of box 1 and the possible outcomes of box 2 here. So the possible outcomes for box 1 are 1, 2, 3, 4, 5. And the possible outcomes for box 2 are 1, 2, 3, 4. I need to center this. So if I wanted just the possible outcomes using matrix notation, I take the first I take the first entry from the row and the second from the column. Okay, so those are all the possible outcomes. I'll be satisfied if you write that. And then you mention, so the outcomes of interest is a set of numbers on the two balls that are chosen. What is the sample space? So these are all the possible outcomes, and that's it. Now, they wrote them in curly brackets, but this should be fine. Okay. Now, so that was just the first exercise where X is, the outcome would be the numbers on two balls that are chosen from one from each of the boxes. So the next one, I'm going to be more explicit. X is the sum of the numbers on the two balls selected. So I don't want just what balls are selected, I want their sum. So I'm going to do this again. This is a new variable. No, I didn't want to do that. All right, sorry. Play with this. Okay, so for this one, I'm going to use more color. So box 1, box 2, so now I want the sum. So if I sum these, this becomes 2, 3, 4, 5. This becomes 3, 4, 5, 6. This is 4, 5, 6, 7. And 5, 6, 7, 8. And 6, 7, 8, 9. And now so X is the sum of the numbers on the two selected balls. Find the probability distribution. So what I have to do is find what's a distribution. It's a list of all possible outcomes, and a probability distribution includes their probability of occurrence, the likelihood of seeing them, and how often we see it. So these are all the possible outcomes. But I can group them because there's more than one there's more than one way to get 3 or 4 or 5 or 6 or 7 or 8. So that increases the probability of getting a 3 or a 4 or 5. Now, in case of all possible outcomes, there are here 20 possible outcomes, and each are equally likely. We know that the possible outcomes, their probabilities must sum to 1. So each has a 1 in 20 chance. So then for these, the probability that x takes little x is what we want to display. We want to depict that. So the possible outcomes for x are 2, 3, 4, 5. Six, 7, 8, and 9, right? 2 has a 1 in 20 chance because there's only one of the outcomes. 3 has a 2 in 20 chance because there are 2. For 4, it's 3 in 20. For 5, it's 4 in 20. And for 6, it's 4 in 20. And 7, it's 3 in 20. 8 is 2 in 20. And 9 is 1 in 20. And those total to 1. So I just leave it as fractions. It's just easier for me to sum them. It's easier for me to just add those and make sure they add to 20. All right, so that's 8, 14, 20. So that's the second part completed. Questions? So this is the probability distribution of x. All right, no questions? So what next? So we did this. Find now the events, the following events, and their probabilities. So what I'm going to do is take these 2 questions onto another page and make some more drawings, similar drawings. So let's make that one more time. So I'm going to make the sum, right? 1, 2, 3, 4. 1, 2, 3, 4, 5. So this is 2, 3, 4, 5, 3, 4, 5, 6, 3, no, 4, 5. 4, 5, 6, 7, 5, 6, 7, 8. Six, 7, 8, 9. So the ball drawn from the first box is an even number, would be this row and this row. Those are all the possible outcomes of the ball drawn from the first box is even. So that's going to be green. And blue will be, B will be sum is odd. So yeah, I'll use blue. Sum is odd. So which ones will that be? It will be these, and these, and these, and that. So that will be blue. And the sum is 9. I will use red. So we have a color-coded map now. So I want to figure out the probability of A, B, and C. Can you guys help me? So A is the green ones. Oh, I shouldn't circle that, should I? Because that's just, I'm going to erase that. That's the number. That's not an outcome. So what's the chance of the green outcomes? 4 out of 20. So the probability of A is 4 out of 20. I'll just leave it like that for now. The probability of B, so I'm going to put it again, A is the green. The probability of B, the blue, is 1, 2, so just count them up, right? It's 10 out of 20. And then the probability of C, which is the red, is just 1 out of 20. Now, some of these events overlap. You see green and red overlapping sometimes. You see the red and the blue overlapping as well. So we have some overlapping events. We have between these three events. The question becomes, are they independent if they're overlapping? We need to check that. We also want to know about any pair that's disjoint. So what we're going to do is look at all the combinations, A and B, A and C, and B and C. Oh, sorry, yeah, 8 out of 20. I don't know, not counting properly here. Okay, so this 8 is the green. I don't know why I put 4. So that's it. I'm a little bit distracted here. All right, so let's see. Let's take A and B first. And what's the chance of A intersecting with B? So that happened here, 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 and here, right? So that's yellow. And there's 4 out of 20. So the question is, they intersect means that the events overlap. So is this overlapping event, well, the joint event, is that are they not only overlapping, but are they independent events? That becomes the question. So to check for independence, so if it's true that this value, 420 out of 20, is the same as A times B, then they are independent. So let's check. So I showed you how to do this the other day. I'll say I'll take the left-hand side is P, A, and B, which we just looked at the table, our model here, and we calculated on our own. That's 4 out of 20. On the right-hand side, what just happened? So now on the right hand side is PA times PB. So what is that? A was 8 out of 20 and B was 10 out of 20, which gives, well, I'm not going to multiply them. I'm going to use some canceling here. So this will cancel with that and leave 2. And this will cancel with that and leave 2, and 5. So we end up with 2 out of 10. Did I do something wrong? A is 8 out of 20, 10 out of 20, 2, 2, 2 out of 10. No, that's correct. So isn't this also 2 out of 10? Or 1.5 or 0.2? So I'll just write as 0.2 from here. So it turns out that the left-hand side is equal to the right-hand side. So yes, independent. So that's how you check. You set it up as if it is, and then you check to see the left side and the right side if they're the same, and they are. So now what I want to do is visualize that, use the drawing to see that. So if you look here, how do we see that? Overall, the chance of A is 8 out of 20. And the chance of B is 1/2. I can reduce those a little bit. So B overall is a 50% chance of being in B. And for being in A, it's not going to be so meaningful, but okay, I'll leave it like that. My point is that it's half. So for B, it's half. 50-50 chance of being in the blue. Now, if you look at being in A, the green, notice that the yellows are half of the green. So what does that mean? It means when I go into the subset of A, the green, the chance of B didn't change. It's still 50%. Okay? So I convert this to the yellow is A and B. And the chance of B overall is 50%. And even in the subset of A, which is just the green, it's also 50%. So that shows you, that demonstrates that they're independent. The probability of B didn't change when I was in A. Now let's do it the other way around. What if I'm in B? So being in B is the blue. So the chance of A is 8 out of 20, or 0.4, right? Overall. And inside of the blue, what's the chance of A? So inside of the blue, to get the ratio of A, these 4 out of a total of 10, 4 out of 10 is still 0.4. So this demonstrates that we don't need to, it doesn't matter if we condition on B, the probability of A is the same. It didn't change inside of B. And we also did probability of B in A. When you're in A, the chance of B is 4 out of 8, which is still 50%, which is the probability of B. So nothing changed. So those are two ways to show independence. You can show that these are the same. It doesn't matter that we condition, we still get the answer for A's probability. And it doesn't matter if we condition on A, we still get the chance of B's probability being the same. In the subset or overall, it doesn't matter. It doesn't change the probability. Okay, so that's that. So A and B are independent. And then what about A and C? Oh, what just happened? Oh, sorry. All right. So let's look at A and C. I'm going to take these away to another page. So the chance of A and C, where is that? A is green and C is red. Do they ever overlap? No, they don't. So A and C are disjoint. You never see the green overlap with the red. And finally, what about B and C? The blue and the red, yes, they do overlap, and they are 1 out of 20. So now that it's overlapping, we can ask the question, is it independent? We can check. If A and C are independent, then the probability of A and C must equal the probability of A times the probability of C. So we check on the left-hand side. Where the probability of A and C is 120. Oh, I said B and C. I changed it. No, A and C. Why did I say that? B and C, B and C. Are you guys watching? This is B and C. So let's check the right-hand side. The right-hand side is the probability of B times the probability of C. The probability of B is 10 out of 20. And the probability of C is 1 out of 20. So certainly they're not the same. So it does look like A, B, and C are not independent. They're just overlapping. Therefore, B and C are not independent. They're just overlapping. Any questions? So also you can see that B is 1 out of 20. I mean, C is 1 out of 20 overall. What about when we're in the blue, subset of B? If I'm in the blue, C is not 1 out of 20. It becomes 1 out of 10. So those are not the same. So you can also check. Oh, yeah. That's the one? So the probability of B is 50%. But that's not the same as being in C and the chance of B. What's the chance of being B inside of C? So if you're inside of C, what's the chance of being B? So in the subset of C, what's the chance of being B, also in B? It's actually 100%. Because B inside of C is all of C. So this is 1. And they're not the same. All right, so that's that exercise. And then there's some visualizations, like they put them together as events, and they show you that A and B are overlapping. They don't show you the demonstration, but when it comes to B and C, they mention that C is completely inside of B. So this is not, these are not even overlapping events. It's an enclosed event. So this is similar to the fifth case that we dealt with in the class, in the lecture. Questions? All right, so that's what I wanted to do there. The rest of the exercises you can work with if you haven't already. And that brings us here. So what I did here was solve for the answer to this question about the chance that you have a disease if you have a positive test. And then I went through a roundabout way to get the same answer using Bayes' rule to illustrate how to use Bayes' rule. And I left off with part of it. I wanted to show you that we talked about where all these numbers come from. The only one that was outstanding was this one. And I asked you, where does it come from? How can you find it? And I found it using this table above. Here you have all the possible outcomes, totaling 1. Each of the entries inside the joint distribution, probability distribution, are, so the one that we're interested in, let's just go to that one, not that one. We're interested in this one. This one is probability of positive test and no disease. And that's the one that we need. Now, how would I find it? Well, we were given, if we look back, we did get this information. We got information on the disease, chance of the disease. We got information on the chance of testing positive. And then with that, knowing that, knowing the construct of this table, you can figure out what no disease is by, this is the complement. And then, sorry, not no disease, but negative test. And you can figure out what the chance of no disease is. Now they gave us something else. They gave us also this conditional probability, which you can split up into this. And because of this, you can find out what's the chance of disease and testing positive. So you can find this one. Once you find this, you can find that. Once you find this, you can find that. Once you find this, you can find that. So it's like a step, you can step through this. And fill the table. And when you do that, you get what we need. Well, you didn't have to fill the whole table to get what we needed. But what we needed to find the answer was this one here. And we get it right away. And that's what I use to compute, and then I end up with the same answer. Okay, so I didn't have to do all of this because I had lots of information. I had that critical information about the chance of having the disease. Oh, sorry. You have the chance of having a positive test if you have the disease. That's the number you need. So that Right, that with that information, you're able to fill the table. Because that information leads to this, and since we have this amount and this amount, we can find this amount. So then we get that one, and then because we have that one, we can use the complement to get this one, and because we have this one, we can use the complement to get that one, and so on. But all we really needed was this one. So these are gymnastics, these are practice. You know, it's good to go through the mechanics here to understand what you're doing. There's no other way. The exercises, the quizzes online are very good too. I do a lot of Bayes in there. And then yesterday we talked about the rules of means and variances, and I did quite a bit, and I encourage you to watch that video again. And then I asked you to try this for today. So how did you do here? Were you able to get the answer? So this one doesn't have a solution, so that's why I'm doing it with you. The other ones have solutions. So I'm going to give you 5 minutes. If you didn't do it, try that now. Take a break. Okay? All right, I'm back. How did you do? No answers? I don't see any answers on here. All right. So each year, employees of a large company receive a bonus of $500 plus $100 for each year they have worked for the company. Therefore, we define a variable. If we define a variable X as the number of years employees worked for the company and Y is their bonus, this is the new variable. So we don't need to follow or track this variable for several years. We know about a related variable, and this is known as a linear transformation. I multiply it by a scalar and I add a shift term. So I know how that influences the mean and standard deviation of the new variable. So we're told that mu x is 6.7 years and the mu of y is equal to 2.4 years because x is the number of years an employee works or has worked for the company. So the probability then of y is the probability of 500 plus 100x. What am I doing? Not probability, I want to do e. Do that again. The e of y is going to be the e, so the expected value of y is the expected value of 500 plus 100x. Now the e operator, remember, this is the mean of this is the same as this. So whatever I do to x, I do to the mean. That was the property that we learned here. And so this is 500 plus 100. Oh, this was sigma. Thank you. And this is mu x. So then this is 500 plus 100, 6.7. And what do you get? Now this is in dollars. 1,170 is the new mean, or the mean of the bonus. And what about the standard deviation? So the variance, we're going to begin with the variance of y. Oh, something happened. My connection broke? No. I'm not sure why I'm buffering. Okay, I'm back. So the variance of y is equal to the variance but we discussed this, that the variance operator eliminates the constant. It doesn't, variance is not influenced by a shift term. It's just influenced by the scalar term. And so this becomes 100 squared times variance of x, and we already know what that is. So that's 100 squared times sigma x squared. I don't know, that I keep on messing up with that. That's sigma x over there. I have to rewrite it, so messy. Sigma x. So this would be 100 squared times sigma x squared, but what I want to do is really the standard deviation. I want to calculate that. So sigma y, or I could also call this mu y, sigma y is just the standard deviation, so it's the square root of that is 100 times sigma x, which is 100 times 2.4. So the standard deviation, which is all I wanted, is $240. It's a tight distribution. Any questions? So those are my answers. The mean and the standard deviation. And that's all I want to say. So you need to practice these and let me know if you have any trouble. On the final exam, I will expect you to do a problem similar to one of these. That will be in the breakdown of the final exam. So you need to practice those, and you should practice them now while it's fresh in your mind. Okay? All right, so with that, let's move to binomial now. So it's 7:30, so yeah, we have enough time. That's not it. We have enough time to cover bin. And the thing about bin, the homework for bin solutions I've provided in a document, so you can check all your worked out solutions in detail. Actually, I have all the solutions posted on the site, but let me see if I can show you. So So here, so this is the homework set of homework solutions to all the problems document. And then in bin, uh-oh, what happened? Did I lose connection? I don't know why I have to scroll again, but okay, so here's bin, and here I have the solution. So I have the homework solutions worked out completely here for you. And I think it's a similar document in the other list of homework exercises, okay? So you guys can go through all of those when I'm done. There's some videos here as well. And for tomorrow, if you can, oops, I want you to watch those SDS videos. Right, so I want you to watch, yeah, all these for tomorrow, these videos here. All right, so then tomorrow's just a review. So let's get to the notes. So if you remember, a binomial distribution has two parameters, n and p, and they perfectly define the binomial distribution, and I promised you that with that information we'd be able to calculate probabilities of certain outcomes, and I'm going to demonstrate the pattern or the formula, the binomial formula that helps us do that. The binomial random variable is defined as the number of successes observed in n independent trials. That's a general statement. And this will be the case provided these three criteria are met. First, each time you observe a trial, the chance of finding what you look for, the success, there are only two possibilities, the chance of a success or that of a failure. Second, the probability that a success occurs on each trial is known, and we use the symbol P for it, but we should know it. And third, X is defined, the third point is that the number of trials is known and these trials are independent from each other. It means that the probability P is the same on every trial, it doesn't change. This is a loaded statement. Okay. Yes, Unit 5 videos for tomorrow, if you can. If you can't, then you watch them after the class. So, for example, n different people randomly selected and observed to determine whether they are divorced. That's an example. Well, counting the number of people that are actually divorced among all the people that you asked, that is a random variable, random variable. Second example, n different light bulbs are randomly selected off an assembly line to determine whether they are defective or not. So even though we're looking for defective, and even in the first one we're looking for people who are divorced, we still call it a success. It's not a normative term. We're not judging people. We're just using the term success to identify what we're looking for. Okay, so let's begin where we're headed. This is where we're headed. This is the binomial formula here in the box. this above is the probability distribution where I show all the possible outcomes for x. So x could be no successes all the way up to n successes. So there's n plus 1 possible outcomes. Now, where does this come from? This is the question. I'm going to show you how I derive that variable. That formula. And I think I'm going to do it by example, and then we'll go back and review the theory, okay? So here is an example. If a fair die is rolled 6 times, the probability of obtaining exactly 1/5 is equal to, okay, so this is a binomial because I can identify the parameters and x as the number of successes in n trials that are independent. How many times will I repeat the identical trials? I'm going to roll a die 6 times, so that's the number of times. And what is the success? What am I looking for? Each time I roll the die, what am I looking for? So the term exactly 1/5 is referring to the outcome of all of the trials, because x could be 0, 1, 2, 3, 4, 5, or 6 5s. And I'm only interested in exactly 1/5. So each time that I roll, what am I looking for? What am I counting? I'm counting 5s, not and so each time I roll the die, I'm looking for 5. I'll just say a 5. Or just 5. Okay, so looking for a 5. I'm going to put those quotes just so that you remember it's the number 5. So each time I roll, I'm looking for a 5. So what's the probability of a 5? So P is the probability of getting a 5. Each time I try. No idea. The probability of a 5 is 1 out of 6. So each time I roll the die, the chance of seeing a 5 is 1/6. That's different than saying after you rolled all the die, how many were 5s? That's the question about X. So overall, this is the chance of getting the success each try. These are the possibilities for after I've rolled the die 6 times, I could see 0, 5s, 1, 5, all the way up to 6 5s. There are 7 possible outcomes. From the 6 trials. So what I'm interested in is the exactly 1 5. I want to see what's the chance of getting exactly 1. Now the probability distribution for this would include the probability of getting 0, the probability of getting 1, the probability of getting 2, all these probabilities. I just want this one. So how many different ways are there to see 1 5 in 6 rolls? The first roll could be a success. But then the rest would all have to be failures. Right? So this one would be a 5 and all the rest not 5. How else could we see 1 5? Well, the first one would not be a 5, but then the next one would, and the rest would not. That's another way to see it. So how many ways are there of seeing exactly 1 5? Do you guys see this, my point? Now you don't want to have to list this every time. There should be an easier way to be able to count the number of ways. And in fact, there is an easier way. So is everybody okay that they see there's 6 ways? Right. There's 6 ways of having 1, 5. But we don't want to list this every time. So we have a trick. I'll call it a trick. We have a formula. This is known as 6 choose 1. So how many ways, this answers the question, how many ways are there to see 1 success in 6 tries? Well, 1 success, yeah. So the answer is C, choose 1. This is a combinatorics or combination. You should have learned about this somewhere in mathematics, but if you didn't, now you're going to learn. So we write that as 6 choose 1, like a vector. 6 choose 1. And you actually have this symbol on your calculators. I asked you to buy a calculator or get a calculator with this symbol on it, so we can do this very easily. So I'll show you here how I get that answer. See, identify it here. Above the plus is the NCR button. It's the N choose R. So I'm going to hit 6 second NCR 1 and I get 6. Do that again. 6 second function NCR 1 is 6. So that's all it takes. Now in the notes I provide a formula for this, and that formula obviously is programmed into the calculator. You don't have to use the formula, you just have to use your calculator to get it. So there's 6 ways of seeing a success and all the rest failures. And I found it by this combination, or this the value of 6 choose 1. So we write 6, this means 6 choose 1. In general, it's NCR, or in our case we use NCK. So what have we accomplished? So all we found out is that's the number of ways to see a success. Now we have to find the probability of a success. So take any one of these. What's the probability of this occurring? So let's just take one. We don't need to look at all of them because we know they're sick. That's all we know. They're going to be the same probability. So what's the probability of a success? Oh, why is it closing? The probability of a success is 1/6. What's the probability of a failure? Give me the fraction, Valeria, for failure. Very good. So this is the probability of this and this and this and this and this and this. So I multiply all those together. And I'll make that look nicer by using 5/6 to the power 5 and 1/6 to the power 1. And then I have to multiply this by 6 choose 1 because there's 6 ways of doing that. So this is what we found here is the probability that x equals exactly 1. So you can calculate it and then I'll give you the general formula of what we did. So how do we calculate this in our calculator? You shouldn't round anything. You should use your calculator. So we already know that this is 6. We can simplify things. And this is 1 out of 6, so these cancel. And so this is just going to be 5 out of 6 to the power 5. And that's it. 5 divided by 6 to the power 5. .4019. So we don't want to have to do this every time. We're just going to use a general formula. So I'm going to derive the general formula from what we just did. And then you have to apply it every time. Once you know you have a binomial variable, you can apply this formula. Questions? Okay, I know I went too fast. So 5 divided by 6 equals y to the x 5. Is that okay? All right, so now let's make the general formula from this. Let me take this away. So in general, I said we need x, n, p, and k. K is the number of successes in n independent trials. N is the number of trials. P is the probability of success. And K is the any combination of x equals 0, 1, 2, 3, 4, 5, or 6 in our case, but I'm going to say to n. Okay. Now you can just use one like we just did at a time, but you could use a combination. So in general, we write the probability x equals k. I'll say any of, or any combination of them. So in general, if you just use one at a time, notice this was n choose k in that case. So it's going to be n choose k, the number of ways of seeing k successes in n trials. Times the probability of success p to the number of successes k. And then remember what we had to do. We had to multiply all these probabilities because there were, yes, there's the success, but then there's all the failures. So how many failures are there in general? And what is the probability of a failure? The probability of failure is 1 minus p. And the number of failures, well, if k are successes, then n minus k are failures. So what you see is these sum to n, and these must sum to 1. That's the formula every time. So that's just calculating the probability for one of all of these possible things here. All possible outcomes. But as you see over here, the probability distribution lists all the possible probabilities we could solve. So we made the general formula, and then you see it here when x is 0, or k is 0, right? When k is 0, this becomes a 0, this becomes a 0. So no successes means all of them are failures, so n failures. Well, what is n? N is the independent trials. says here. The number of trials. So when x is 1, k is 1, then it's one success, and then n minus 1 failures. All right, so this is the general formula for the whole probability distribution, and I've justified it, so let's just keep on applying it until you get it. And I'll say some things about it tomorrow once you've practiced and become more familiar with this. So you have all the solutions to all of this. I have given you them. So let's start here because I filled that space. We already know the answer to that because that's about the two heads observing. No fewer than two heads. When we toss a coin, you can try that one on your own. So what about 3? Suppose that 60% of a herd of cattle is infected with a disease. So X is the random variable representing the number of cattle that are infected. If a sample of size 5, in a sample size 5, let Y denote the number of cattle that are not infected. So what's the distribution of Y? So X would be binomial because I could identify N and P. Well, actually, they don't give me N and P, but in Y, they tell me what N is. So this is my N, size 5. And P, well, I know that the probability of disease is equal to 60%. So the probability of no disease is equal to 40%. So this must be P. So Y is random variable with N of 5 and P of 0.4. So B is the answer. Very good. Okay, let's go to the next one. So when you solve these problems, to identify if they're binomial, try and answer this. All right, how you doing? Did you do it? Okay, so what is X here? So I look for what I'm interested in from the question. Here's the question. The probability that 6 patients or less die. So I'm looking for death, unfortunately. So what I'm going to get is the number of patients that die out of the total. So there's 7. So whatever I write here, I put it here. And X can be 0, 1, 2, 3, up to 7. Well, actually, I want to write them all down. Let me do that again. The probability that someone dies and unfortunately success is death. The chance that they die of the fever is 70%. Wow. Very high. So we want to answer the question, what's the probability that 6 or less die? 6 or less dying is going to be all those. So a better way to do this, a more efficient way, is calculating the probability that 7 die and subtracting that from 1. Much more efficient. So to get the probability that 7 die, then we use that formula that we have above. Or just our logic. Let's just use our logic. So we know that we want to know how many ways are there of seeing 7 successes in 7 trials. Let's see. 1, 2, 3, 4, 5, 6, 7. And all of them are successes. How many ways of seeing that? It's just one way, right? So it turns out whenever you use the n here, if it's n choose n, it's always going to be 1. Similarly, when you have n choose 1, it's always going to be, or n choose 0 is always going to be 1 as well. So we'll talk about that more tomorrow. I'll do some more in-depth look at this. Then I have to multiply by the probability of success and how many successes, because I want to multiply them all together here, right? So there's only, well, there's 7 successes, and then failures, there's no failures. So this is what I'm going to calculate. This is 1. This is 1, this is 1, and all that's left is this. So the chance is 0.7 to the 7. Now we're not finished. We have to go answer the question. This was just for the probability of 7. We need to take that from 1. What do you get? %. Any questions about that? So 91.7%? Yeah. Or 92. Okay? Very good. All right, let's do the next one. Let's do one more and then we're going to go. Or maybe 2 more. So try this. Okay, so how is K defined here? K is the what you're looking for. It's the number of successes you're looking for. It's X. So X is the number of successes out of n tries. So in the problem here, we're looking at 4 patients, and the chance and the success we're looking for is that they is sufficient staff. So we have to look at the way the question was phrased to find what we're looking for. So sufficient staff. No. That's the overall answer. No, that's not right. Each time we look to see if a patient requires attention. That didn't work that time, did it? So patient requires attention. Let me rewrite that in black. So this is a statement about each time. Each time you look at a patient, each trial. The success is patient requires attention. K is out of all, after all the trials. What are we looking for? What is, I say K, the special K. This is the thing we're looking for. So to not have sufficient staff, where we assume that you need at least one member to attend to a patient, So assuming that you need one staff member for patients to attend to an emergency, and there's 4 patients, and 2 staff members, if more than 2 need a staff member, you're not going to have sufficient staff. So in this case, after all trials, insufficient staff is K, really. K has to capture what insufficient staff means. So insufficient staff would be 3 or 4 people requiring attention. That would be a problem. That would be insufficient staff. So what's the chance of success needing attention? It's 0.3. So whatever you are given here as your probability is the one that you're going to use. As your success. All right, is that clear, Valeria? So K is what you're interested in, what you're looking for. Oh, it's not going to fit. It's very important that you get K, so it's good that you're asking. Basically, K is what you're looking for after all the trials. So P is the probability of success on each trial, but after all of the trials, what you're looking for is K. So X could be 0, 1, 2, 3, 4 in this case. So K is which one of these you're looking for to answer the question. So for sufficient staff or insufficient staff, which of the X's imply insufficient staff? Well, if 3 or 4 require attention, that's going to be insufficient staff. This was a little more complex one. You can think about this a little bit more, but it helps you realize where you get it and where you don't. So each time we repeat a trial, there's a chance of seeing what we are looking for, the success. Out of all the trials, what are we looking for? Well, in this problem, we're looking for 3 and 4. So we have to use the formula for 3, and we have to use the formula for 4, and we have to add them together. So let's do that. So for 3 successes, the chance of a success is 0.3, and we want to see if there's, we want the 3 successes, and then that leaves 1 failure. What's a failure? It's 0.7 to the 1. Remembering that these must add to n, and these must add to a total of 1. And here it's going to be 4 successes, and then because there's 4 trials and 4 successes, there are no failures. So these sum to 1, and these to 4. So calculating here, simplifying a bit, this one is a 1 because I already described how many ways are there of seeing 4 successes out of 4, just one way. And when you use 4 choose 3, we already did that one too. I mean, well, we did it with 6, but it's going to be 4 because we just distribute, or we just cycle through the one success, or the one failure in this case, and that's going to be 4 ways of seeing that. Or you can use your calculator if you want. You can verify. So get these 2 things. This one is going to be 1, and multiply. So I'll multiply it with you. So 4 times 0.3 to the power 3 times 0.7. No, it doesn't. This calculator doesn't use order of operations, so you need to use the brackets. So 4 times 0.3, 4 times bracket 0.3 to the power yeah. So 0.3 to the power 3 times 0.7. Do it again. 4 times bracket 0.3 to the power 3 close times bracket 0.7. Oh, I didn't have to use brackets because it's just a 0.7. So that's 0.0756. And then this one will just be 0.3 to the power 4. Point 0.0081. Unless I made a mistake, that's the answer. Let's see, 0.0837, so it would be B if I got it right. I did get it right. So that is it for today. Continue to practice this unit bin for binomial. Go back and look at probability some more. Review the exercises towards the end that review the rules for means and variances, and let me know if you have any questions tomorrow. So otherwise, I'm just going to do some touching overview of the binomial. Watch the SDS videos that I have in Moodle. And then tomorrow we're going to dive into sampling distribution of a statistic, SDS, and maybe touch inference, maybe. Any questions for me? Well, you should do all the bin exercises here and watch those videos and make sure you reviewed probability enough. So yeah, just a review of everything. But yeah, the new stuff would be the SDS videos, if you have time. Okay, so good night. Bye for now.